location tag from your GPS to their website. And that's the only reason I got a phone that had a GPS in it, and a web browser, and all the rest of that crap.
Yeah.
You are alive.
Yeah, my flip phone was getting obsolete. I wanted to move it to Verizon network because Verizon has better reception in places where I often go. AT&T has just, the populated areas. Verizon has all kinds of places that you couldn't get AT&T right. Except for emergency stuff. Okay.
Who else is watching me? Somebody's watching me. 2 people are watching.
Wow. We haven't even started yet.
We haven't even started. Wonder.
I got your YouTube message.
You did?
And the audio is good.
And the audio is good.
So
oh, I send messages now?
When it starts up, it sends a message.
I changed my settings recently, and I noticed that.
It's been sending messages though for a while.
Then I don't have to.
Well, to YouTube.
I don't know if this is the plug-in one.
If you send messages to like email addresses, that's different.
Floppy drive in.
Oh yeah, I had a laptop like that. Okay,
so that worked.
Oh, it had a floppy, a CD, and an extra battery.
I'll get it.
Oh, so.
But those plugins, you can run those on a USB cable too.
Oh, if you have the right connector, usually.
It's a regular connector. If you look at the plugins, you'll see they have a standard USB end on it.
Oh.
And you check the audio, but we don't have audio. Or do we? Did he leave it on?
Yeah.
Oh yes, he left it on.
You can have your CD player in, and then plug in your floppy drive.
Yeah, I'm getting a little bit. Okay.
That's pretty clever.
Right. The ones that I had was a specialized connector.
Yeah, there's a specialized connector to go into the machine.
Right.
But if you look on the side, there's a USB connector.
I never saw that.
No, I'm pretty sure.
I have those computers in the alley, but So 2 weeks ago, I was at the last day of HSC.
Oh yeah, I just couldn't bring myself to go. First off, the way that they did
there he is.
movie.
How you doing?
Good.
The science fiction movie, the Langoliers. For your motorcycle helmet. That's what I call it. If you're the Langoliers that hangs around a little too long, and you just get bunched up. And that's what happened to HSC. I never had one too long. I'll show them. I won't wear it bunched up. You never had that feeling. When you first passed a lot. I know. I think it's long, but I never said. I think I'll go put this on. You said me.
那么这里面它可以很 好几首歌在里面。好，这个太久了，要把它关掉。好，这一开机的时候，它就会有些 noise。200 init。
这不能看，这不能看。
啊？
在电脑上不能看。
我现在就在控制它。OK。所以它这个一开机的它有一些 noise， 这是我因为这个我的程式要把每一个 device 都在 initialize 的时候，对声音并没有太注意，所以我这个刚刚给一个让这个100init， 这样就 initialize 所有的这个 output， 那么 hush 就全部停掉啊，所以这个是，那么这个，我现在这里面所有的所有 compile 的指令都在这里。对，你看这个就是这个音符，就是哆来咪发嗦。这是怎么样子演奏？这个 M1、M2、这些就是乐里面一个小节一个小节，我每一个小节扣它几个小节起来。OK。是歌了。我应该3条的，就3条。FIG 是它一步慢慢进来，就是这个buffer写很多风景曲都用这个方式。FIG 1。第一步。第二步。2个是。3步。它这4步进来都做了，然后它就做各种变化。好了，太长了，这个把它停掉吧。我现在这里没有办法停它，所以只能够从外面停。你要把这些重新 initialize。OK， 这个是这个所有的程式是这个样子做。OK， 我们肯定要开始了。
先回去。
啊，对，啊，没事。I think so. Do I have it? Okay, all right. Okay. Still got 1 minute. Or are we? 2 minutes. 1 minute. Okay. Okay. Yes.
When is the Maker Faire?
Maker Faire will be May, the last week of the May.
Yeah, we'll have everything running perfect.
Okay, I hope. But I need some pictures. Do you have pictures?
No, we're gonna have robots running around.
But you know the application.
Oh.
So I have the application. And I think we have to send in 2 weeks. So.
Can we update the picture later on?
I think so, but if we have anything, I think it just your old the whisker will be quite adequate.
I'll take a picture of whiskers.
You have the manual.
No, I'll take a picture of whiskers, the one that I have.
Okay.
And
Yeah.
I'll give that to you, and I'll give you the manual.
Yeah. I think you gave me the manual, the general description and the programming manual, but I misplaced them. So send again.
Okay.
Yeah, with a good picture.
Okay, I'll do that.
Yeah, great.
No later than end of the day tomorrow.
Yeah, let's. I think we probably can talk a little bit about Maker Faire this afternoon, and see. I have the application. I failed it the first round, but I think we need to talk a little bit about it. See if we can put in a real strong application and get the boost we want.
So everyone sitting here, you're all work programmers. We'd love to have help at the Maker Faire.
Yeah.
There's going to be a lot of
Yeah.
people, and we need to give them a little basic
Yeah.
my course is more English top level, but
as Megan coaches you, I have different
Yeah.
hours.
Right. So we generally Maker Faire will give us 5 free tickets for the helpers.
okay, great.
Yeah, and that's about the $50 worth, or more. Yeah. So I think if we get the booth, we'll get 5 tickets, and then we still have a few discount that we can buy. All right, let's get started. Hello, everybody. Let me see. Welcome to Silicon Valley 4th Interest Group, and this is the first meeting of the year. And I'm CH and this I will talk about the ESP4, and a little bit. It is designed for the AR robot down the building. So I think I promised to talk more about Arduino interface this morning. So I'll do that first, and then I'll show you some the progress I have with the ESP32forth. So this morning I talk a little bit about the NodeMCU, and this is the little module. Yeah, that's currently sold. I bought it at Amazon for about $10, but I look at eBay, it's $5. So it's $3. Okay, wow. Yeah, this module is very nice, but you just plug in the USB and it will work. And so I talked a little bit about ESP32forth and Arduino IDE. This is the first major topic this morning. And what I found is that actually execute individual genome commands in Windows. And so that was very nice. And I was able to use it to force it to spit out the assembly code and all the interesting things, which I want to learn about this, the underlying CPU. So I show you a little bit about the ESP32forth machine code as compiled with the C compiler. And I'll do a little demo on this Arduino IDE with ESP4. And I don't have a robot to program, so I did an 8-channel electronic organ, because this chip has 28 or 28 I/O pins. And most of them, you can use them to drive the LED drive motors and produce square waves and all these kind of things. And I found that there are 8 channels. I can control them individually. So I can produce 8 voices. And that's just perfect for my electronic organ. I've been trying to use all the different microcontrollers to play box music. And this chip is the first one to succeed. Okay. And the earlier, I have to use PC or big computers to do that. Okay, I'll also give you a little demo of the organ. Okay, ESP32. 3 years ago, we were using the ESP8266. And this was the theme we had for the 2017 Maker Faire. Okay, so I think we gave out 50 of these modules to students who succeeded in talking to things through the Wi-Fi. But this chip, this module, it's slightly bigger, I think twice bigger and twice more powerful. And it got many more I/O pins and probably many more I/O devices inside. So I think it has 2 CPUs, 2 32-bit CPUs in it, and lots of memory, lots of I/O, and ADC, DAC, UART, SPI, I2C, Wi-Fi, and Bluetooth. So all these things on the same chip. So that makes it very interesting. This is the picture of the module. I think this module costs right now $10, $5. It's a very nice module. You plug in something and it generally works. So you don't have to worry about the USB interface and all the other things. ESP32 is twice more powerful than ESP8266, and it is ideally suitable for an intelligent robot. And 3 years ago, I tried many different IDEs, and now I think I don't have all the time to test out any other thing. So I just pick Arduino IDE and try to get deeper into this system. So I've modified ESP for the 8266 and get it to work on the ESP32. And you need to change only one command, and which is the .h file, the Wi-Fi.h. So in the ESP8266, you need 8266 Wi-Fi.h, and you just delete ESP8266, and it will work on ESP32. So that was very pleasant. But I think 3 years ago, I basically decided not to work on this chip anymore because I was worried. This chip has Wi-Fi built in, so every chip you can talk to it through internet, and you don't know what's underneath this chip. And I'm worried that if there's something built into this chip, and at the height of the US and China trade war, they might invoke one command. And I think there are millions and millions of these chips in the US. and it might just caught up all the 8266 and do something. And you can imagine what a disaster that would be.
How about bricking the chip? Bricking it, making it, dead.
Well, yeah, you can break it, but it would never work again. Okay, yeah. But without the complete knowledge of the ROM inside, I do not trust these chips. So I told myself, that's it. We ran the maker fair successfully, but that's it. I don't want to do anything more on it. So I gave up all my ESP32 kits that the Taiwanese friend sent me. And I said, oh, okay, that's it. I don't even want to touch ESP32. But then Don came along and said, oh, let's build a robot. And what kind of controller can we use? And said, well, you can't beat this one. Okay, so let's do it. But never tested it. Okay, let's do it, and let's get the robot to work. Yeah, but
So you don't have any more insight into the ESP32 ROM than you did into the ESP8266?
No. I don't have any knowledge of the underneath system.
Can't you break one open and read it?
Well, I can actually. I was able to read the entire ROM, everything. I was able to read it, but I don't understand it. Okay. Yes.
I've had experience with that kind of thing with the wireless, both at Marvell and at TI.
Yeah.
And oh yeah, I'll work on the driver, like a Linux driver for it. But boy, they say you are not looking at what goes inside.
Right.
Absolutely not.
Well,
Now,
but you can.
Let me explain that a little bit further.
Yeah.
There is inside every SoC, and almost every microcontroller has a very small portion of ROM that is basically a bootloader.
Right.
That allows you to Arduino to talk to it.
Yeah. Right.
And that you can flash things onto it.
Yeah. Right.
That is not very big and probably not very dangerous. But you can't get
You
source.
don't know.
You don't know. Correct. You do not. You never get source code on any microcontroller of its ROM.
Yes.
You never get it. So if that's true of every microcontroller. Now I do have the entire stack for this M5. This is M5 stack. The company that made this one is ExpressIF.
Yes.
And they have tons of documentation. They have a full stack of their effectively Linux stack. I've got all of that source code.
Yeah.
I would suspect most of it's open source. It comes out of the Linux.
Yes.
It's basically an embedded Linux.
Okay. Let's don't. Yeah. Let's don't worry about that. But just to say that we can use it to our heart's desire, but don't trust it. Okay. Until you know exactly what goes into the ROM. Okay, so this is the a picture of the I/O on this chip. You can see lots of different things, and these many pins you can use as analog input, and most of the other ones you can use as GPIO, and they have some touchpad capability built into several of the I/O pins. So very powerful, very useful, and especially for a robotic program. So ESP32forth and this ESP32 8266 with a change of one word. Okay, and this force basically it emulates EP32. It was a 32-bit fourth microcontroller. So I basically took the design of ESP and wrote the design in C, okay, and put it so this C program was compiled onto many different things, including Windows. So it is written in C as a sketch on Arduino IDE, and the Arduino IDE it runs on many different microprocessors. You need to extend IDE, include the ESP-specific tool chain to work with this chain. Okay, I just want to show you one thing about ESP Finite State Machine. Okay, the Finite State Machine expressed in C is okay. So it's reading bytes, reading characters from this C data array, and then execute the bytecode. Okay, and it pick up because P++ is incremented, so it's ready to execute next one. So you just keep on doing that, and that's the finite state machine. Okay, very interesting. In that C is kind of capable of doing all these very nice things by itself. So the Arduino IDE, it seems to be the IDE for all microcontrollers, especially for the Windows environment. And the sketches are the C++-like programs, very easy to write, even for beginners, because it has only two keys to write. You have a setup, and you okay. You just write these two, put in some C++ code into these two loops, and it will do everything. It's magic. But its tool chain is very complicated. Okay, it's generally hidden. You basically you just clip this upload key, and it just happened everything, and eventually the code it generates is flashed into the microprocessor, and it executes subsequently. So it is the user interface is genius, okay, and it reduced the C programming to two routines. So I think it's even okay. So I'm trying to get to the bottom of these things, and because the whole thing generally is compiled with GNU tool chain, and probably in the Linux environment, and I never can set up my computer to do Linux. I can use lots of help. Okay. Okay, and but you know, in exploring all the various capabilities, I found that if you set the verbose mode in the compiling and in the flashing, it will spit out all the commands that it executes. And this verbose output, you can just copy the entire thing and store them into a batch file. I think I do a little bit of editing because the file name are mostly inside double quotes. So I just delete all the double quotes and put in name the file .batch, and double click on the batch file, and lo and behold, the whole thing is execute faithfully in a command window. Okay, and generally the command window would, after it finished, and the command window will be closed automatically. If you put a pause at the end of the .batch file, you stop there, and then you can look at all the output. So that is what I found, and I think many of people are interested in that. So just try to do it yourself, and you can explore the Arduino IDE to the next level, to the command code level. Okay. So you in the big file, you can see there are lines of commands. If you just copy individual lines of the command and put copy the individual command into separate .batch file, and you can just exercise that particular command. You can do assembly, you can do compile, you can do link, and you can do all the individual things that you are interested in, which the entire system hide them from you. So I want to look at the machine code, because after all the compilation and linking, the final link command, you cut out that link command and put this dash WA comma dash 8 this option into this command, and it would just spit out the entire machine code at you. But it goes out too quick, too fast, too big. You just can't handle it visually. So at the end of this command, I put in greater than ASM.text, and so this send out in a pipe to a text file, and then I can open up that text file and look at all the commands in my leisure. So I think this is the secret. Okay, one of the secrets. Okay. So once you can manage the individual build command or batch command, then you can explore things more closely without a Linux system. Okay, on Windows alone, just make batch files. So what I'm interested in is the Xtensa machine code. I have I will talk about peek and poke. Let me see. Let me just go through the slides. Not getting ahead of myself. Xtensa is a CPU architecture originally designed by Cadence, and the Cadence sell this design to anybody who want to pay them money. I don't know how much, but Tensilica took the design and designed actual chips. Okay, and I think the Express just somehow bought the rights to the design and build this chip, build the module and chip. So this Xtensa CPU, it is a RISC-like 32-bit core, but the instruction set is 24 bits. Okay, and just like ARM chips, that you have ARM instruction set and you have the thumb instruction set, but because they realize 32-bit is just too big, and you don't have that much information in that 32-bit. So you can reduce the size of the instructions by throughout many other fields that you really don't need. And they are doing the same thing And many of the instructions, they have what they call the 16-bit narrow instructions. They just keep, in a 24-bit instruction, you have 6 4-bit fields. And many of the instructions use 3 fields for 3 registers. So you have source 1, source 2, and target. Okay. But most of them, you don't need 3 register references. You have 1 source, 2 source, and one of the source can be a target. Okay, that's how we do most of the things. So throw away one register field, throw away some other information, and you can reduce the 24-bit instructions into 16-bit instructions. I was first I was able to peek and poke and look at the entire memory and look at the code. And because this code are variable length, so some of the instructions are 24 bits, some of them are 16 bits, and all the data are 32-bit aligned to cell memory. So you have 3 different things in the memory, and it was very difficult to see what's going on. So I look at all this code. Lots of things I can recognize. These are addresses, 32-bit addresses. Okay, so that's addresses, and I think it's mostly the code, and code don't know. But realize that there is most of the code has an ending 1DF0. Okay, so this thing kind of occurred in the memory. 1DF0 somehow in the 32-bit field. Sometimes you get 1D, sometimes you get 1DF0, sometimes you get 1DF0 and something else. And I think, yeah, that's return, okay? So that's the only thing I can recognize in the. But then, if I have, so I was very anxious to see how the code actually look. So the machine code, let me talk a little bit. At the architecture, it has 16 registers, so that there's a 4-bit register field to be referenced. And the machine code is very difficult to read because instructions are of variable length. Those data are always aligned to 32-bit cells. And another thing I didn't fight for is that it implements stack windows or windowed stack. Okay, it has window stack design in the architecture. So when the call, you can call simple call, just go into one routine, or you can set up stack frame to pass parameters into and out of that particular subroutine. So this is what I found, because I'm looking at, I just compiled the source code. I found where forth is, and was able to read some of the all machine code that's being compiled. So in forth, the most important instruction is next. How do you go from one? You compile a list of instructions, pseudo instruction. How do you go from one instruction to the next? Okay. So this is how it was compiled. So LC0, LC1, LC2, and LC3. These are references to the 4 registers in the fourth machine. So 4 registers we have for the stack pointer, return stack pointer, and the WP, IP, and the WP. So these are the 4 registers I need to go from 1/4 word to the next, and it was compiled this way. Because in 4th, these things will be in the registers. Okay, so the code could be much simpler, but because it's compiled by C, and C has its convention of passing. Oh, that's okay. That's okay. That's okay. For C convention, parameters from one routine to the other. So when it follows the routine, things get very complicated. So if I will be writing this thing in 4th and use machine code, probably can get rid of 2/3 of the instruction. So this is artificial intelligence, okay? That's if you want to do everything, that's what the machine can do. But you look at it yourself, that's dumb, okay? But that's artificial intelligence. So exit is this way, and you can see that some of the instructions are 16 bits, and mostly in a have a .n in it. It will force the instruction into 16-bit form, okay, if it can. Okay. So, but you can see in the disassembled fashion, you can see everything. But when it is in the memory, you really don't know what you are looking at, okay? Because it's and okay. Now let me just do a little demo on the IDE and show you what I have.
Dr. Tim?
Yes.
Is this a 16 or 32-bit port?
This is 32-bit.
Okay.
Yeah. Mm-hmm. The 4th is 32-bit. It's a token with byte tokens. Okay, so each 32-bit word contains 4 individual byte code. Okay, so that's the at the low level of this virtual machine. Okay, let's see. I want to show you the IDE. Okay, took the thing and turn it on. It does not turn on. So it was just looping there, looking for the Wi-Fi station in my home. Okay, and it couldn't find it, so it just keep on looking. I have to recompile the whole thing to take out the Wi-Fi initial routines. Okay, so this is the in verbose mode. It spelled out all the commands that it executed to build the entire system. And it's just doing the. You can see it first executes. I don't know what it executes. I was expecting a makefile, but I could never find a makefile. I think the makefile is contained in these executables. And then it says detecting a library used. So it did libraries and generating function prototypes, compiling sketch. So here it starts to compile the sketch and compile libraries. And it found that it needs the Wi-Fi. So it compiles a huge thing for the Wi-Fi. And so let's don't, and you can see that with all the reference, basically it just goes through the chain of 5 folders, finally it found the G++. Okay, this is what it executes. And then this line is extremely long, okay? Let me show you how long this thing is. So you go through, each reference has a reference of the file. So you can see it just goes down, finding all the files it needs, and with all the options. And it just goes on and on and on and on and on and on. Finally, okay. So you can see, you got your Unix guys knows what's going on. It basically compiles things and generate an O or C. It pre-processes a lot of files for the Wi-Fi, and for the other things, you can see it generates the .O files. Okay, so here it compiles things, and finally each module it generates .O the assembled file. Okay, and then later on it takes all these files and build. Take all the .O files, okay, and do all the interesting things. Okay, let me just show you the finally the linking. Okay, so this is the more interesting thing. So there, we generate all the object files and then link everything together. And then it calls ESP tool, which flashes the code into the chip. And once it's everything's compiled, and then it starts flashing. Okay, and this flashing code because I have including the Wi-Fi. Yes.
Arduino IDE compatible loader, or does it just load it with the basic? In other words, so you need a loader put in your device.
Yes.
Correct.
Yes.
Okay.
Yes.
You don't have to because it comes with the Arduino loader.
Yeah. It has a tool chain. So it can deal with different microcontrollers differently.
Well, Express IF has a version that just.
And I this you can see the characters in red, but that's okay. That's okay. Don't worry. Don't worry. Don't worry.
I'm not worried.
Yeah. So here. Okay, can you see better there? This way. What I want to show you is this. So it compiles. The entire thing is 677,648 bytes. So the whole thing is 600 kilobytes. Yeah. But this guy got lots of memory, so it doesn't worry. Yes. 677,000. Okay. But don't worry. It has enough memory so far. Okay, so that's the Arduino interface, and because although it's huge, I think this chip, somewhere I said that it is designed for Unix. Okay, it is a mainframe computer designed for Unix.
Is the reset working for you?
The reset. Okay.
Last line.
Yes. Reset work itself. Okay.
It doesn't dial.
But you need to push down the program button.
Interesting.
Yeah. When it starts when it starts flashing, it will give you some dots for you to push down that 0, yeah. So you have to hold that key down to start. Okay. So that's one thing I
Software reset doesn't always work.
Yeah.
And so maybe you should just hit the button again.
Okay. Yeah.
That's
So,
what I have to do.
yeah.
Yeah, it's supposed to work, but it doesn't.
Yeah.
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 It works on some of the chips.
Yeah.
That's what's funny.
Yeah. The for the AVR chip, it starts download immediately and everything comes up. But this one you have to hold down the program key for it to download. So that's one thing I struggle with when nothing works. It doesn't want to flash, and it just show me the dot. I say, what is it? Finally, I start to push all the buttons, and finally, you have to hold this right-hand button down. Okay, so let's go back to my on current side. Okay, so I think this demo I want to show you the Arduino IDE, show you the sketch. Oh, I haven't show you the sketch, but I show you the Verbose and compile, upload, and GCC command sequence. Now let me show you the serial output. Let me see. Okay, so here is the sketch. So here is the fourth sketch. Okay. It's small. Okay, it's not that big. Okay. Let me see how many lines. 547 lines. So that's not too bad, right? But the reason it has only 500 lines is because I put the dictionary in a separate file. Okay, here this is a dictionary. Okay, and dictionary has I allowed 16,000 words, so that's about basically 64 kilobytes. And if I do the 16384, it will crash. Okay, it doesn't want to read that big a file. But if I just reduce all the 384 bytes, 384 words, and the Arduino will take it comfortably. Okay, so I don't know why. Yeah, apparently the arrays, you cannot have arrays bigger than 64K. Okay, and so that's one problem. We may not have to. So this is the dictionary. Okay, and the dictionary has how many lines? 15,000 lines. So that's but most of them are zeros. So depend upon how big the you compiled. Okay, so this is the sketch. Okay, and now let me show you the this is the serial monitor. Okay. Okay, you hit return and and then do words. Okay, So here I have compiled three fugues into the system. So the fourth itself, I think it is forget code. Yeah, that's the top of the ESP32forth, and everything else is compiled on top of it as an application. So you see, I'm compiling all the nodes, and nodes just are frequencies that you want to play on each and every different channels. And then 1/4, this is the quarter note. If you want to play a chord for quarter note, half note, whole note, 1/6. So all these things are redefined as fourth commands, and you can play chords up to voices. So you can specify an 8-voice chord to play out. And I redefined 1, 2, 3, 4, 5, 7, and 404, 140. And these are, because I only have 4 channels, and these are the ones to specify which channels I want the nodes to go into. Okay. And with all these things, I can compile measures, and then I can compile phrases, and I can combine all the phrases into a piece. And this is how you can code a very complicated music this way. Yes. Okay. So let me just play one piece, and maybe just a few lines of a piece to show you the 4-channel capability. Let me see. Let's. Okay, fugue 1. In my old implementation on PC, inside 64K, I was able to compile 5 fugues. And fugues are big pieces, okay? But here, it crashed if I tried to compile that many. And finally, I found that I can only compile 3 of them, okay? And that basically fills up the 64 bytes array. So fugue 1 is one of them. Let's see. Okay. Sorry, when this resets, it initializes things in a different strange way. So if I should have initialized this way, oh, sorry, 100. Okay, so if I put in a node that the 100 hex frequency, 256 cycles per second, and initialize all 8 channels, but you don't want to hear anything, so hush would silence everything. Okay, so that's how things work.
How many speakers do you have?
I have a few slides on the organ, so I can show you. Okay, let's just get rid of that. I have done all the demos that need to be done. So I close everything and go from here. Okay. So peek and poke. So this is the ESP32forth is a virtual machine implemented in C. It addresses 64K of virtual memory. That's as much the compiler allow me. Okay, and the peek and poke, on the other hand, it addresses the absolute memory. Okay, so I really don't know where this virtual fourth array is located. So I have to find it. But the peek and poke allows me to address absolute memory. And this way I can look at the entire memory map and see where things are. So it took a while to explore 64 megabytes of memory. So peek and poke, that's the code. I think John probably can explain it better. But the peek and poke would go to the absolute address instead of the virtual memory address. Okay. So with that, I can explore all the memory and the I/O space. Okay. So here are some of the primitives I used to play the music. Pin is to pin select. So this machine, they designed such that there's lots of functions, lots of I/O functions, and lots of pins. And you can connect, you can assign many different functions to a particular pin. So this is what this pin command would do. Okay, basically it's in the system is called attach. You can attach a function to a particular pin. And here I'm attach the counter timer or pulse width modulation output to 8 different pins. Yes.
So you put the pointer to the function on top of the stack,
then the pin number.
Called a number.
Yeah.
Oh, okay.
Okay.
I see.
Yeah. So this is the C code. The LEDC attach pin, that's the C code. It takes the 2 parameters. The top is I forgot the top is the function, and the next one is WP, which is the number. Okay. Okay, one is the pin and the other is the function. And then the duty is actually calling the analog write. So the Arduino system uses digital I/O as analog output. And it just assigns a different duty cycle to a PWM wave. And this way you can vary the brightness of an LED. That's what they call the LEDC. So it's controlling LED pulse width modulation. But you can set the duty cycle with the duty command. You can select the frequency with the frequency command. And all this these C routines will be called. These are made to be the forth tokens and can be executed from forth. And the forth can through these functions calling the underlying tuples. Okay, so this is audio, which generates tone, and the send packet, and I have the UDC. I have implement UDC, so I can actually send out UDC packets. And the receiving side of forth would accept UDP packet as well as input from the serial. So ADC, you can generate true analog signals through the pins that you assigned. So these are the once I have this duty, frequency, tone, pin, ADC. These are defined as bytecode, and in forth interactively, you can exercise these low level functions by a code function in code. You have the bytecode there, and then you have the next bytecode so that it can execute the forth commands smoothly. So, and the GPIO, to GPIO, it has lots of registers. The GPIO, it has two ports, P0 and P1. P0 basically is a 32-bit port, 32-bit port that you can read, you can write, and you have different ways to enable it to set up each different pins as an output or an input, and you can actually set this pin, and all this, or you can set and clear all the pins at the same time. However, the P1 port has only 8 bits, okay? So mostly they use this 8 bits as the analog input. Their default, they are connected to analog input, okay? So that's the P1 and P2. Most of these 40 pins are brought to the edge. I think 28 pins, 28 of these signals are brought to the edge. So this is my electronic organ. So we have this chip. There are a set of resistors behind it on this board. I'll show you that. But you know, generally, earlier I was sending out each of these digital signals to a speaker. As you remember, in the 1984, 85, when I play this thing, I have to bring out 6 speakers to play the thing. But now these speakers are really nice. $15 for one, and they made these speakers for Bluetooth. So if you put Bluetooth in it, you can play anything. Speaker. So here I just use a resistor network to combine the 8 output into 2 left and right, 2 voice channel output. So this is how this thing is done. And I use 8 of the set up 8 to output PW pulse width modulation waves, and they are combined, sum up in this node, and with all the resistors are 100K. The speaker seems to like that, and then you have left, right, and ground. So I don't have to bring 6 speakers with me, and 1 speaker would work just fine. Okay, this is if I pull out the SP, you can see the resistors are here, and 4 resistors are summed together here, going into the left channel. 4 of them sum here and go to the right channel. So that's my electronic organ. Okay, this is the code to play out 1 notes, play out or I think 4 channels. So you have 4 frequencies and a mask, and the mask defines which of these 4 channels would go up into the lower or upper 8 channels of the output. Have up to four nodes into the lower channel, and then you have another node put out the 4 nodes to the upper channel. Okay, and then you fall into a loop, and I found that 10 million empty loops is equivalent to a quarter node. Okay, so just delay that many cycles, you get yourself. So here init would just copy the frequency into same items on the top of stack and play out all these nodes to all the 8 channels. And hush would put a 0 out. It's interesting. 4 channels would take 0 as an input and stop the channel. But the other 4 input would not. I was struggling here a long time. Because they are basically the structure of the system. It has let me see, 8 oscillators, 8 counter timers, and each counter timer output to 2 PW pulse width modulation pins. So 2 pins share the same frequency from oscillator. So, but there are 2 8-channel oscillators. One they call the high frequency channel, and one they call the low frequency channel. Apparently, these 2 high frequency channel and low frequency channel are designed by 2 different engineers, and they use different command, different things. So, you know, one of the, I think it's a high frequency channels. If you put a 0 as a frequency, it will stop. But the low frequency channel, it requires much more steps to turn things off. So that's it. I think here in the code, you see. I used in one for the high frequency channel, I use tone. For the low frequency channel, duty. I have to use the duty cycle to set up the duty cycle 0 to assign. I don't know why they do this. I think my conclusion is that the 2 engineers work on different so they decide to do things differently. They don't talk to each other. Okay, and then the frequency was all defined. These are quite accurate. You just give it the frequency and it will play out that voice. And then I can set up the nodes. So if I set up all the different things with a mask, and I say, okay, go play out a quarter node, just PPQ, PPQN. This is generally 1 million, 10 million. Okay, that's a quarter node. So you longer or play it shorter, you just scale the output of PPQN. That's a pulse per quarter node. Okay, that's the delay between 2 nodes. If you have to play them as quarter nodes. Okay, then with all these things, then you can write out a piece. So here you can specify. So here, this cord has 2 nodes, and the 2 nodes go to the first and second channel, and you play it as a. So this one you can specify up to 8 frequencies, but the frequency has to be specified the mask, which one goes into which channel. Okay, so I have already demonstrated that. You all hear that? Questions? Yes.
Have you thought about actually using the processor's got enormous speed? You should be able to instead of putting out square wave tones, you should be able to put out the harmonics in steps. You know, just slight modification to your resistors, but pre-calculate what each band's going to be for each of the harmonics.
Yeah,
and you should be able to put out probably 20.
Yeah. If you want to do it in software, be my guest. Okay. It has 2 DAC. It has 2 DAC output. Okay. So you can use that 2 DAC and synthesize or specify whatever the waveform you wanted. This thing has plenty of cycles to do anything.
It's got lots of speed. I mean, you'd be able to easily.
Yeah, I think the one thing you might do is to synthesize voice. Okay, but I think Ron, Don, do you want a voice output?
Yeah, that would be great.
Jack's had a question,
Yes,
and
yeah.
then we should get to lunch.
Yeah. Okay.
Take you about a week.
Yeah.
You said we distributed at Maker Faire, and I'm wondering who we is. I wasn't. Who is we?
Silicon Valley 4th Inches Group.
I see you had a booth there.
Yeah, well, we apply for a booth, and if we get it, we'll do these demos.
Was it last year or the year before that they
The year
called
before.
us ne'er-do-wells and said be gone?
Mm-hmm.
I think we applied. We've had a booth for a few years, and then there was sort of a lull in the action. I think they said, "Oh, we want people that were more exciting and less
Yeah.
thingy."
Yeah, well, I went back.
And less exciting than we wanted.
Yeah, back. We have booth 2012, 2013, and 2017. Okay, thank you very much.
Language that we weren't hands-on enough, or we're not hip enough. Okay.
Okay, thank you very much.
Fire on the table, like the
I was thinking like one of these water blaster cans.
We are going to lunch now. We'll talk to you after lunch. Thanks.